All right, let me try another one here. How about chapter 37, number 48. And number 48 has this source. They do say the wavelength is 500 nanometers in the description of the problem. And they put a screen way over here at 100 meters. But they also put a little mirror down here, so that the reason you would get any kind of interference pattern is because you would get your two sources. One would be the direct shot of the light hitting the screen, and the other one would be the reflection off the mirror. And maybe the important thing to get started really is going back to chapter 36 and realize then that you actually have then the equivalent of a double slit here, because we learned in chapter 6 that for a flat mirror there is an image. And the image is defined as where the light appears to be coming from. And so this reflected one you could think of as coming from right here. And so I'll just make an open circle here. But I would say then these are my two sources of light. And the reason there's an interference is that there is two sources that are a total of 2 centimeters apart that are heading towards this screen. And so that's really the crutch of the problem. It's really a Young's double slit, except to understand that you have two sources, you have to go back to chapter 36. So it ties chapter 36 together here with 37. But it also does one more thing that isn't so obvious, because this light isn't really coming from here. It's actually reflecting off. And so remember, there's a phase change. So keep that in mind, because when we did the Young's double slit, we said d sine theta equals an integer number of wavelengths. These would be the locations where you would get your bright spots, your constructive interference, and you would get your destructive interference at these spots. These are your minimums. And if we truly had two sources, that would be true, but we don't. What we have is two sources with an added phase change. And so what would have been constructive interference, because we said that this is that extra distance that the second one travels, that's why we have constructive interference. You can then say because of the phase shift, it's like another half of wavelength. And so instead of having constructive, we get destructive, and instead of having destructive, we get constructive. And so this was first done by Lloyd, so this is called the Lloyd's mirror. It's the equivalent of the Young's double slit experiment, but it is a little different. So keeping that in mind, I'm going to circle this. This is the equation I want for finding minimums, and that's what this problem says. This problem says find the distance y. Okay, so this is y. Find the distance y, let me just read it here. Find the distance y to the first dark band. Okay, so the first dark band would be m equal to 1. And so d sine theta is equal to 1 wavelength. Or solving the math, sine theta would be lambda over d. And the lambda, as we said, is the 500 times 10 to the minus 9, because it's nanometers. And the distance, as we said, is 2 centimeters. And 2 goes into 500, 250 times 10 to the minus 7, or maybe I'll just write it as 2.5 times 10 to the minus 5. And that would be sine theta. So then if we go inverse sine, and of course we could do it in degrees or radians, but I think it's probably more appropriate in this case to do radians. because for small angles, one of the small angle approximations, and we did way back when we did the pendulum, but also true here, this chapter, is that in small angle approximation, the sine of the angle and the angle are pretty much the same thing. Now that becomes useful because now if we come back to this picture and we say, okay, let's think of this then as a distance along an arc, S, r theta. R is this radius, which is about 100 meters. And the angle that we're talking about along this arc is what this means. So 2.5 times 10 to the minus 5 radians. And then that just makes 2.5 times 10 to the minus 3 meters, which we can write as millimeters. So 2.5 millimeters. And so that's the height up, 2.5 millimeters.